Hi everyone. This will be the last video I make on Lebesgue integration unless you guys have topics you'd like me to cover. Just leave those in the comments. In this video, I'll just go over important results. We won't prove anything. So this first one, I'll just put zeros on them because there are a bunch of sort of very, very basic results that are relatively intuitive and often are left as exercises to the reader in books. So first of all, this is actually a definition. We say that two functions f and g are equal almost everywhere if f times the indicator function on z complement equals g times the indicator function on z complement, where the measure of z is 0. So they're equal everywhere except for a set of measure 0. So an immediate consequence of that is that f and g being equal almost everywhere tells us that their integrals are equal, where this is again Lebesgue integral. Similarly, if I give you f that maps into non-negative reals, then it's equal to 0, f is equal to 0 almost everywhere if and only if its integral is equal to 0. Finally, next. So these are good to just write down and just know them. So this is another definition. So now I'm ready to consider f mapping from the reals into the reals, where we now possibly have negative values. So we define it as let f plus be the positive part, aka the absolute value of f, and f minus to be the negative part. So whenever f is negative, we flip its sign. That's why this is negative f. Otherwise, we set it as 0 if we're positive, right? Because if f were positive, this is a negative number, and the maximum of those two is 0. So then we say it's Lebesgue integrable if each of these components is integrable and at least one of their expressions is finite. So one of them can be infinite, but they can't both be infinite, because if they're both infinite, then this expression here is infinity minus infinity, and we don't know how to define it. So that's all there is to that, natural extension. And then this last part is just a bunch of properties that they hold for Riemann integration, and you use them when you do Riemann integration stuff, so they all hold for the Lebesgue integral. So if I have a bound on f, and I consider an integral over a finite measure set, then a times the measure of that set is less than or equal to the function defined or integrated over that set, which is less than or equal to the upper bound. Relatively intuitive. F is less than or equal to g implies their integrals preserve this property. That's often called monotonicity. If I multiply by a scalar, I can pull it out. And if I add two functions, I can pull them across, aka the Lebesgue integral this integral operator I is linear, is what that is saying. This is something you've probably seen tons of times in your analysis career to this point. The absolute value of the integral is less than or equal to the integral of the absolute value. Also holds for Lebesgue integration. And then if I consider a smaller subset for a non-negative function, then I can only add positive values to it, so I should preserve this, this equality as well. So just remember that it's indicator function. So this is really a corollary of monotonicity, because this is defined as multiplying by a characteristic function on a possibly bigger set. And then similarly, if I give you that a set E is a disjoint union of measurable sets, then I can just split across that union. So those are sort of basic properties. And now I'll state 5 major theorems that come up over and over. Carthy-Theodori's extension theorem doesn't come up too much. At least it hasn't for me. Maybe there's people in the literature that study it religiously. But this is just something that I've brushed over. We could have built this theory. I just didn't feel like doing it. But we've been working on the Borel sigma algebra, but the Lebesgue integrals can actually be defined on a slightly bigger set, sigma algebra, and that is through Carthy-Theodori's extension theorem. I don't state this here because it's somewhat more complicated, but I'll just show you how it works, specifically in the case of the Borel sigma algebra. So M is our Lebesgue measure. Then I can actually measure any subset of the reals through this outer measure. This is called an outer measure. And all it says is that if you give me this set, I cover it with a union of things that I know are measurable, and then I take the sum of those measurable sets, and that defines a measure. You can check that. And then I take its infimum, right? Because obviously I could just take the reals, in which case it covers everything, and then it's boring. Everything's infinite. So this expression can still be infinite, even if this infimum... So for example, the measure of the real line is infinite, right? Because the only way that I can cover it, that expression has to be infinite. So its infimum is infinite. Then our sigma algebra, so our sigma algebra is then defined via, it's a set of all E such that this property holds for every subset of the real line. And then this sigma algebra contains the Borel sigma algebra. So this is just a trick that this defines a sigma algebra, and that gives you a natural extension. That's all that's happening there. So just keep in mind that you can actually measure sets slightly bigger, a bigger class through this other operator, M star. The second one I'd like to go over is Fatou's lemma. So this is just a good tool to have for when you're proving sequences of things. All it says is that if I give you a sequence of non-negative measurable functions, then the integral of the lim inf is less than or equal to the lim inf of the integral. So it's just a nice bounding theorem to hold in your pocket. 3, this is probably the most important one you'll have, that you'll use probably the most. Let Fn be a sequence of measurable functions that converge pointwise almost everywhere to a function f. Again, so this is everywhere except a set of measure 0. If there exists a Lebesgue integrable function such that its absolute value has finite Lebesgue integral, then f is Lebesgue integrable, and with its absolute value having integral less than infinity, and you get convergence of this. So you don't need that the fn's are monotonically increasing, like you do with, or non-decreasing, like with the monotone convergence theorem. So I believe, if I recall correctly, the proof of this actually uses the monotone convergence theorem. But the point is, all you need is a dominating function g. So you'll sometimes see this g referred to as a dominating function. Dominated convergence theorem. The next one you might use about as much as dominated convergence theorem. It is the Fubini theorem, which you probably learned in Calc 3. Holds also for Lebesgue integrals. So I'm going to define I1 to be this expression. So this is just the double integral defined on the product space. This one is dx dy. This one is dy dx. And then these are their absolute values. So I need the absolute values of these to be finite. So if all I have to do is show that one of them is finite, the absolute value, then each of them are absolutely integrable. So all I have to do is show one, and boom, these expressions are all equal to each other. That's Fubini's theorem in the most general case. So in Calc 3, you probably assumed f was continuous. This is a much more general framework. And then the last one that you'll probably use the most in probability theory, but you'll use it sometimes in I guess, quote-unquote, traditional functional analysis that isn't necessarily probability theory. But it's Chebyshev's inequality. So if I give you a non-negative function and a subset of the real line that's measurable, then, and again, this could be in the extended sigma algebra that we mentioned before. So anytime I say measurable, really what you mean is that extended sigma algebra, but you can think of it as Borel sets, like, because that's, yeah, in general, you just have to keep in mind, well, it's technically a slightly different sigma algebra. Then the measure of the set where f is greater than alpha, which is just this pre-image, is less than or equal to 1 over that alpha times the integral of f of x dx. And so in probability theory, it's a bound on the tail of a probability density. But then, of course, we have discontinuities and all this stuff, and you eventually get into distribution, so this doesn't even necessarily have to be a density, but you can think of it as a density function. That just gives you a bound, so it's often used for those types of things. It's also useful in traditional functional analysis as well, where you don't have necessarily well-behaved tail-end behavior, but you have some properties, then you can use this result. That's the way to think about it. Is it's a way to bound the tail of a distribution or any function, a probability density function, or just really any function. I mean, not distribution. So thank you guys for watching. Again, I intend this to close the series. Sort of, it's I do this part just to show you this isn't necessarily a complete course, but those are the main building blocks that you'd need to go forward and to keep in mind, to sort of have in your mind. Those 5 theorems are nice to know. Thank you guys for watching and getting to this point in the series as well. Thanks.